Alright, in this video we're going to be looking at the different number systems that we can use, and specifically ones that are more interesting for digital electronics like binary and hexadecimal. So the three that we're going to look at are decimal, binary and hexadecimal. And the difference between these are the base, or is known as the base. Where decimal is base 10, binary is base 2, and hexadecimal is base 16. And what this basically means is how many different characters, or digits you may prefer, are represented by that number system. Now in decimal we have, as we all know, 0 through to 9. Now it's obvious that we don't go up to 10 because, including 0, there are 10 digits here, not counting up to 10. In binary we have 0 and 1, and in hexadecimal we have 0 through to 9, and then A, B, C, D, E, F. So for one character or one number in decimal we can represent 10 different possibilities. Alright, base 10. In binary we can represent 2 possibilities, and in hexadecimal we can represent 16 possibilities. Noting that effectively these numbers correspond from 10 through to 15. Now the one that's most interesting to us in digital is binary. And the reason for that is the two states look like off and on, or 0 volts, 5 volts, 3.3 volts, etc. Right, so in a electronic system where we want to still be able to use numbers, binary is actually a much more convenient way of representing numbers. You can imagine if we were to use decimal, that if 0 was 0 volts and 9 was 5 volts, we'd have to have every other combination. So 5, or between 4 and 5 would be 2.5 volts, and this might be 1.25 volts, and so forth. So it'd all be quite messy and quite sensitive to noise. Right? Small changes in voltage could cause quite large changes here. So binary is by far the most robust method for us in digital electronics. What's important is that you guys know how to be able to move between these different systems, the decimal, the binary, and the hexadecimal. So, for example, if I have the number, let's say 4 in decimal, I'm going to keep these columns so you know which system I'm using. Okay, or I could put a little 10 underneath like that to say I'm using a base 10. In binary, to be able to represent that, I can only use the values 0 and 1. Because of that, I need to be able to use more than one character, or more than one digit, to be able to represent the number 4. And what we do is the same thing that happens in decimal, is we actually have the 10 to the power of 0 column, 10 to the power of 1, 10 to the power of 2, and so forth. Right? Whereas I had, for example, 34, you know, because this number is in the second column over, it's corresponding to 30, not 3 and 4. Right? 3 times 10 plus 4 times 1. Same thing applies for our binary system. We have 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3, and so forth, going in that direction. In this case, 4 is equal to 2 to the 2. So in binary, this would be equal to 1, 0, 0, base 2. Alright, so that would be 1's column, 2's column, 4's column, and so forth, 8's column moving along. In hexadecimal, we have 16 to 0, 16 to 2, 16 to 3 column, and so forth, going in this direction. So noting that in this case 4 times 16 to the power of 0. Alright, so 4 times 10 to the power of 0 equals 4. 1 times 2 to the 2 plus 0 times 2 to the 1 plus 0 times 2 to the 0 equals 4. And 4 times 16 to the power of 0 equals 4. So in all cases we have represented the same number, 4, but in different number systems. Alright, so let's have a look again at a slightly larger number. In this case, let's have a look at the number 12. Okay, so that's 12 base 10. 10 to the zeros column, 10 to the ones column. So it's effectively saying, although you probably don't think of it when you look at it, 1 times 10 to the 1 plus 2 times 10 to the 0 equals 12. In binary, to get to the number of bits or binary digits, it's another one if you haven't, okay, you probably all know bits, short for binary digits. What you can do is you can work out how many bits will I need to represent a decimal number or a base 10 number. Okay, and so you can work out where n is the number of bits minus 1 is the greatest number that you can represent with that number of bits. Okay, 2 to the power of n minus 1. So in this case, if n was equal to 3, like we had up here, the greatest number, 2 to the power of 3, that we could represent, minus 1, 2 to the power of 3 is 8, minus 1 is 7, which makes sense. 4 plus 2 plus 1 is 7. So we know that we're going to need 2 to the power of 4 is 16, minus 1 is 15. In this case, the answer is equal to 4 bits will be required. So let's work this one out. I'm going to cheat, I know what the answer is, but let's just have a look how that was worked out. So we've got the corresponding columns with the corresponding weights above them, 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3. So in this case we have 2 to the 3 plus 2 to the 1. Alright, so that equals 8 plus, oh, I've made a mistake, 1, 0. 2 to the 3 plus 2 to the 2, 8 plus 4 equals 12. So in binary, the solution is 1100. Alright, and get in the hang of realizing that the leftmost column, or the leftmost number, is what we call the most significant bit. Alright, the most significant bit having the one with the highest weighting associated with it. The one on the right always starts at 0. Right, so 0, 1, 2, 3, and so forth. So if you end up 10 columns along, then you're going to be in the 2 to the 9, for example, because we're starting at 0 there, obviously. And then doing it again in the hexadecimal form. Alright, how many hexadecimal digits do we need? Well, we can use the same formula. 16 to the power of n minus 1 is the greatest number that we can represent with n digits. In this case, if n is equal to 1, you get 16 to the power of 1, which is 16 minus 1 is 15, it would be the greatest. 12 is less than 15, so we can use only one hexadecimal number. So in this case, we would use, we'd go up here to my little table, 12 is equal to C in hexadecimal. Right, so just bring that across there. We'll see that decimal 12 is equal to 1100 in binary, which is equal to C in hexadecimal. Right, and it helps to actually write down a table with each of these in them. So you get a feel for how these look. So 0, 1, 2, 3, and then I'm going to skip through 9, 10, 11, we'll do these ones, 12, 13, 14, 15. We'll go right up to 16. So this is our decimal or base 10 column. This will be our binary column, and this will be our hexadecimal. Okay, binary 0, hexadecimal 0. In fact, hexadecimal is easy. It continues. We just have to use the numbers or the letters all the way through until we get to 10. We'll come back to this interesting one shortly. Binary, okay, and then 9 in binary will be 8 plus not 4 plus not 2 plus 1. 10, 11, 12, 13, 14, 15, and then finally 16. We need an extra column. So I can add in leading zeros, still the same number effectively, remembering that this is the 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3, 2 to the 4's column. 2 to the power of 4 times 1 is 16, hence this number here. For this one, remember that this is the 16 to the power of 0 column, and this is the 16 to the power of 1's column. 1 times 16 to the power of 1 is 16, plus 0 times 1, hence why we need 2 characters or 2 digits in hexadecimal to represent 16. Finally, going between hexadecimal numbers, when they get larger, there's a little trick that I use. So quite often you'll see it prefixed like this, for example 0x34, and I normally break this into 2 parts. Alright, so for hexadecimal number signified by the X, I actually break that into 2 4-bit numbers. 3 in binary, 0011, and 4 in binary. So that would be equal to, in binary, 0011 and 0100 as a complete binary number. So I actually treat them as 2 pairs of 4-bit numbers, alright, to be able to convert between them. And I find that much easier. So similarly again, OXFA, for example, break it in half. F is 1111, A is 10, so 1010, 8 plus 2, so that equals, in binary, that number there. So it's quite easy to move between those forms. To move between binary and decimal, or hexadecimal and decimal, is a little bit more tricky. You can either use your calculator for it, or work it out. So in this case, F times 16, so 15 times 16 plus 10 times 1, and that will give us 250. Right, well in this case we get 3 times 16, so that's decimal, put D or put a 10 down there, 3 times 16 plus 4 times 1, and that gives us 1848, 52. So, just to cover what we've seen in this video, there are 3 standard number systems that we can use. The numbers that you represent in decimal, okay, our normal counting system, or base 10, can be represented equally in binary or hexadecimal. It's the same number, just represented different ways. Just like the same word could be said in English, or Arabic, or French, or Spanish, and all have the same meaning, okay? These are just different ways of having the same number. Decimal goes from 0 to 9, binary from 0 to 1, and hexadecimal from 0 to F, where you see the letters A to F represent the numbers 10 to 15. Right, there's also octal, which is base 8, but a little bit unusual, so we're just going to skip that for now. We saw that binary was the more useful one, given they're off and on, two discrete logic states, therefore being digital, are easier to implement. So in hardware, you'll often see binary, although the same number viewed in binary could also be viewed in hexadecimal or decimal. Alright, it just so happens that working between binary and hexadecimal is easier, as we saw down here, than trying to do these multiplications out down here. Converting between the numbers, right, just looking at the column weights, or the multipliers associated with each one, to be able to convert between the different numbers. And we saw that for a couple of examples here. Remembering that formula, the greatest number that you can represent using a particular base is the base raised to the number of bits or digits minus 1. So for binary, 2 to the power of 3 minus 1 would give you, greatest number would be equal to 7. 8 minus 1 is 7. Okay, and let's say if we had 1 hexadecimal, the greatest number would be 15. Alright, 16 to the power of 1 minus 1 is 15. And then we had a look at how they would all be written in a number table there.